this video, we are going to examine uncharged and non-rotating black holes. We will see what it means for the singularity to lie in your future once you cross the event horizon. We already talked a bit about black holes and what it means when our equations break down in previous videos. But now, we will finally change to a coordinate system that is smooth through the event horizon. We will also examine the regions of the maximally extended solution. Let us start by examining what a black hole is. If a mass is compressed to its Schwarzschild radius, it becomes a black hole. The escape velocity at its surface is the speed of light. However, it will become clearer later on why the escape velocity definition is not ideal. Remember that the line element around a spherical, non-rotating, uncharged mass is given by the Schwarzschild metric. We know from previous videos that to find the shape of the light cone, we can set the metric and the angular part d omega to 0 and find dt over dr. As one approaches the event horizon, the light cones become narrower and eventually close completely. If we were far away and watching someone fall into a black hole, we would see them approach the event horizon slower and slower and never actually cross. They would also be redshifted by gravitational redshift. Let us go back to the metric and imagine a person that is hovering just outside the event horizon. In that case, his angular motion and radial motion would be 0. That is, he is only moving through time. If we say the infinitesimal time he measures on his own clock is d tau, then, because the metric is invariant, this would equal the negative of the line element. Tau is called the proper time. T is the coordinate time which in the Schwarzschild metric is the time measured by a faraway observer. We can take the square root and integrate both sides of the equation and get an equation for the proper time. Here we have replaced 2gm with the Schwarzschild radius. The speed of light is set to 1, which is why it is not present. Writing the coordinate time gives us the formula for gravitational time dilation. Let us quickly see how this works. Suppose we are far away from the black hole, and our friend Bob is hovering near the event horizon at r equals 1.1 rs. If Bob in his reference frame emits pulses of light every second, that is, the proper time tau between pulses is 1 second, then we would receive those pulses around every 3 seconds. The pulses would also have their wavelength stretched from gravitational redshift. Of course, as one gets even closer to the event horizon, this becomes much more extreme. At the horizon, you can see that this becomes infinity. Let us return to the Schwarzschild metric. In a previous video, we discussed that although our metric goes to infinity at the event horizon, this is just a consequence of using an unsuitable coordinate system. The event horizon is then called a coordinate singularity, just as the origin is in polar coordinates. A person can easily fall through the event horizon, but the Schwarzschild coordinates cannot be used smoothly to connect the interior and exterior. We will now finally change to a smooth coordinate system. Let us first go back to the equation for the light cones in Schwarzschild coordinates. This is simply a differential equation for the coordinate time t. If we solve this equation for t as a function of r, we get t is equal to plus minus r star plus some constant c. R star is called the tortoise coordinate. This is because r equals 2gm, which is the location of the event horizon, now corresponds to r star equals negative infinity. The location of the event horizon has been pushed away infinitely far, so in a way we approach it more slowly. Let us define the coordinates v as t plus r star and u as t minus r star. We have seen these types of coordinates in the last video. If we solve the v equation for t, then take the derivative and square it, we can put this dt squared back in the original metric to rewrite it in terms of the new coordinate v. It is a bit of lengthy algebra, but the result is the following metric. This is the Eddington-Finkelstein metric. In this coordinate system, we do not have any infinities anymore at the event horizon. You can take the determinant of this metric and plug in r equals rs and see that it is non-zero. These two facts show once and for all that the event horizon was simply a coordinate singularity caused by a poor choice of coordinates. Plugging in r equals 0 still gives an infinity in this metric and will give a zero determinant. There is no coordinate transformation we can do that will remove the singularity at the origin. Let us compute the light cones in this metric. Again, we ignore the angular part and set the metric equal to 0 to find dv over dr. The solution, where dv equals 0, means that one of the directions of the light cone is the coordinate axis itself for all r values. We can plot a VR diagram and see the shape of the light cone. Very far away, that is at r equals infinity, you can see that the second light cone solution is dv over dr equals 2, not 1, like some might expect. At the event horizon, r is equal to rs, which gives an infinite slope. This is a vertical line. Past this point, your fate is sealed. Your future light cone now points towards the singularity. No matter which direction you travel, it will be towards r equals 0. In a way, the time and spatial dimensions have swapped places. Just as you are watching this video and will go to tomorrow, inside the event horizon, tomorrow is the singularity. You can now see why the escape velocity definition of the event horizon does not really work. Even though it is correct that the escape velocity at the horizon is the speed of light, we must have this additional condition that your future lies inside the black hole. Even though this coordinate system is smooth through the event horizon, perhaps we are not done. Remember when we had the tortoise coordinate r star, we defined two variables v and u. We have used the v coordinate in our current metric, but what if instead we had used the u coordinate? V was t plus r star, and u was t minus r star. We can follow the same procedure that we have done to write the metric. If we do, we get a nearly identical metric, but now we have this minus sign. We can once again compute the light cone and see that the minus sign essentially gives the mirror image of the light cone with the v coordinate. Now, inside the black hole, our future points away from the singularity, and after we cross the event horizon, it is no longer possible to enter the black hole. This is therefore not a black hole, but a white hole. We have seemingly discovered a new region. If we go even further and use both v and u coordinates at the same time, then compact our coordinates into a finite value with the exponential function, and then change back into a single time-like component and three space-like components, we end up with Kruskal coordinates. I will simply present the result and how the variables are related to the standard r and t coordinate. This is the maximally extended Schwarzschild solution. In this metric, we have discovered all mathematically possible regions without hitting the singularity. From our last video, we know the process to construct a Penrose diagram. Doing that with the Kruskal metric gives the following Penrose diagram. Light obviously travels at 45 degrees, and the path of an arbitrary person that falls into the black hole is shown. We can say that we have four different regions. Region 1 is outside the black hole. This is where we live. Region 2 is the black hole. Past the event horizon, the light cone points to the singularity. Region 4 is the white hole, a time-reverse region of the black hole. Things can travel into our universe from there, but we cannot get there. It is in our past. Region 3 can be thought of as a parallel universe, a mirror of our universe. It is space-like, separated from us. Travel between Region 1 and 3 is impossible, as one would need to go faster than the speed of light. It is useful to think of the singularity as not like a dot at the center of a black hole, but a space-like surface that all infalling objects will reach. This solution, however, is likely not physically possible. Remember that our solution is a vacuum solution of an eternal black hole. In realistic gravitational collapse that produces a black hole, we expect a Penrose diagram that looks like the following. In particular, there is no parallel universe, or white hole. The shaded orange region is the interior of a star. Since it is not a vacuum region, it is not described by Schwarzschild. From the video about Newton's law in curved space, recall that we solved the geodesic equation for the Schwarzschild metric and found the effective potential V. Let us take the derivative and set it equal to 0. We are essentially finding the maximums and minimums of this function. R has been replaced with RC, which is where circular orbits occur. L is the angular momentum per unit mass. Epsilon is 1 for massive particles and 0 for massless. We have also put a gamma on the general relativistic part of the equation, which we can choose to set to 1 if we are examining the full general relativistic solution and 0 if we are simply examining Newtonian gravity. Setting gamma equal to 1 and finding RC for massive and massless particles, we get the radius of the photon sphere as 1.5 times the Schwarzschild radius. This is where a photon can orbit a black hole in a circle, but it is unstable, so any perturbation will send it into the black hole or off to infinity. For the massive case, 3 times the Schwarzschild radius is the minimum stable circular orbit. Between 1.5 rs and 3 rs, we would have unstable circular orbits for massive particles. There are some things still that we have not covered, such as Hawking radiation and entropy, but these would require separate videos. I have presented some formulas for them here. An interesting one is that of the time to singularity. This is the time it would take to reach the singularity if you were to fall from rest from the event horizon. For a black hole of 1 solar mass, this corresponds to a Schwarzschild radius of about 3 kilometers and a time to singularity of only 15 microseconds. For one of the largest black holes ever found, with a mass of 66 billion solar masses, this would be around 12 days.